problem we have three tanks all side by side, one lower than the other. And we have a flow rate of fluid being poured into each tank, and that tank has a hole in the bottom, filling up the tank. So there's a flow rate coming in to this first tank that I'm going to call Q in, and it's filling up this tank right here, which is causing another flow rate, which I'm going to call Q1, that's pouring in to the container beside it, and that container, and so on and so forth. So we have a flow rate going into there, into this tank, second tank, and then third tank has a flow rate that is just weak. So for this problem, we want to be finding the change in the height in over the change of time. Since each of these height or each of these tanks have some height. So for this first tank, I'm going to call that height 1, second one is height 2, and third one is height 3. So we want to find a differential equation for each of these tanks for which the height is changing over time. So now that we have these tanks, we can see that we're going to have an equation with the left side of our equation. First of all, I'm going to actually denote this area. So we have an area coming, area of our holes at the bottom of our tank, which the fluid's flowing out of each of these tanks. Area 1, 2, and 3. And then we also have a cross-sectional area that we'll need for each of the tanks because we want to find the volume, or we're going to need the volume to find this difference. So we have the cross-sectional area of 1, 2, and 3. AC1, AC2, and AC3. And now we should have all of our variables to start solving for our differential height over our. Okay, so obviously we have we're going to have the change in our height, which is also affecting our volume. So we have AC1. This is for our first tank. We have an AC1 times our differential height, and that's going to be over time, our differential time. So now that we have that, we can set it equal to the other side of the equation. The other side of the equation is going to be our flow rates. Flow rates, for the first one, we know that that's just going to be Q in, since it's just giving us what our initial flow rate will be. And that will be subtracted by the flow rate that's coming out of our container, that's leaving it. And we already know that we derived that in one of the other problems, which we just got as square root of Q times G times H1, since that's the first one, times our area 1, which is our area of our hole with the fluid bleeding. So now we can just take this AC1. I'm just going to erase it on this side since we're going to be dividing it over here. So we 1 over AC1 times our Q in minus our Q1, which is our flow rate. So this is right here. Is our Q1. Like I denoted earlier, it just from the equation that we derived earlier. So it's just going to be our height of the container times our acceleration due to gravity times 2 times the area of the hole. So now we're going to need 2 more differential equations as we need to do the same thing for the other 2 containers that we have. So we have the same thing on this side. Time's going to stay the same, obviously. The time doesn't change between containers, but the height does. So we'll have a different height, and also this AC1, our cross-sectional area, is different in our second container, which is now going to be 2. And instead of Q in, our flow rate that's coming into our second second container is actually Q1. We can see it here, it's just pouring into that. So I'm going to use Q1 here since I already labeled it right there. And that will be minus our second flow rate. And so this will be our differential equation for our second container. And now third container is essentially the same with different height and different flow rate. So that will be times Q2 minus Q3 flow rate coming into the third one is flow rate 2, Q2. And so now we need to label also our Q2 and our Q3 since I don't have that labeled here, but we know that's just going to be a third of 2 times acceleration due to gravity times H2 for Q2 times our area 2, which is our hole coming out of our container, our second container. And third one, same thing, I3. So now that we have our differential equations, we can now code for this and call laboratories. I'm going to switch onto my computer. Okay, so now that we derived our 3 equations, we can now code for all of these in co-laboratory. So I'm going to import my NumPy as MP, so I don't have to keep writing that. We know this is an initial value problem, so we want our initial value problem solver. Oh, I mistyped there. Okay. Okay, yep, that should be good. Right here, I have just a list of the different variables that were given the problem and also the equations for which we solved for earlier. Okay, so our parameters are going to be gravity. Then we have our areas of our holes. Which will all be that. And then we also have the areas of each of our holes. Or sorry, the area 1, 2, and 3 are areas of each of our holes. This is the area of our containers. And finally, we have our initial flow rate. Okay, that looks good. Now we need our heights. Our heights are just found by reorganizing our flow rate equations that we had earlier. So it's going to be flow rate for each of our areas squared. And that will be multiplied by 1 over 2 times. So it should be just for good measure, add 1 more parentheses. This is going to be the same for each of our heights. That's good. Now we want to define our vector, which is just going to be named RHS. It's going to be for variables t and v. And I will define v. V is just going to be those heights. And I want to make sure that my Qn would be equal to that. And okay, now we want each of our flow rates. So we have these equations written down. So this would be Q times G times H1. All that will be multiplied by A1 and Q2. And finally Q3. Okay, now we want to return that as an array. And what's that array going to be? That is going to be each of those part of our problem that's in parentheses, which is going to be, first one will be Qn minus Q1. Q2 minus Q1 minus Q2. And Q2 minus Q3. Okay, so now that we have all of that, I'm going to, sorry, from over page. This needs here. Okay, that all looks good. I'm going to return it in a sec once figure out a little bit more. Okay, so we are back. I just needed to add a few things that I forgot to add, but I put them in here. So there was these three that were part of the equation. These areas of our container, and these three areas also need to be added. And then I had just had a error with H1 0 versus H1. Needed that in there. And also we needed this. We're going to need that later for our subplots that we make for this. So let's get right into solving the actual inequality problem. So first we need our tendency, which I'm going to put as 1,000, since that is specified in the problem. And so let's get our solution. So we want to use our solve underscore IVP, which I imported in earlier for a reason. Then we need our vector. And this is going to be from 0 till that 10. Next, we are going to need, we need to add these variables, which was our H1 0, H2 0, and H3 0. And what do we have? Okay, so next we need, what else do we need? Yeah, so our first solver needs our dense underscore output, which is one thing that you just need to put in for these solvers and make sure that equals true. And the same thing, we need our method is RAID. Okay, that looks good. So now we have our res. We have syntax error somewhere. Oh, I forgot to put a sign in. Um, equal sign. I think this might need to be capitalized. Okay, there we go. I just had a syntax in there, but so now we can get this. This is our solution to our initial value problem. And I'm going to come back in a second and we will be able to plot these. Okay, so now we can start actually making our plot. So first we want to specify our t-plot, which will just be the time part of our plot. So that t-plot will be 0 and 200. MP. Okay. And then we know relationship to solution. Okay. So that's good. Yep. So now we need to make our figure for our plot. So our figure equals make dot or make underscore subplots. So we have that defined. Now we will have figure dot add our scatter, since this will be a scatter plot. And now we could specify our variables. X will just be our time, so t-plot. Then Y will be different for each of one of our heights, but for this first one, we'll just make it H1 and then we can name that. Let's say that's called tank 1. Okay, so now I can just copy and paste these twice for each of our different heights. So we'll change this to our second height and name that tank 2. And this will be height 3, tank 3. Okay, and so this is what we get for our plots. We can see that as time passes, all of our tank heights will just level out. So that's expected. And so yeah, that's what our plot's gonna look like.